Math 1343, confidence intervals, estimating the difference in two populations' proportions. So far we've estimated what percent of a population has a characteristic, but sometimes you want to compare two populations, men versus women, Texans versus Louisianans, if that's the correct word. People with a college degree versus people without a college degree, or any way that you can view parts of a population from two subpopulations, if you will. Let's take a look at this one. In a sample of N1 equals 50 men and N2 equals 40 women. Let me pause here for a second. We're comparing the population of men and women. I'm not trying to draw any conclusion, I just made these numbers up. I have no idea what the answer to the question is because I haven't worked the problem yet. But I'm not trying to imply anything, so you shouldn't infer anything. But the real point I wanted to make is, since we're comparing two populations, we need to pick two samples, one from each population, and it wouldn't be good to use the same letter to represent both sample sizes. A common way to recycle letters is to subscript them. Sometimes the subscripts are generic, like 1 and 2. Sometimes they have more meaning. For example, I could have subscripted this with an M for men and subscripted this with a W for women. But we need something to distinguish between a sample from this population versus a sample from that one. Let's continue. In a sample of N1 equals 50 men and N2 equals 40 women, 10 men and 10 women held 2 or more jobs. Can we conclude at 90% confidence that the percent of all men who hold 2 or more jobs is less than the percent of women? Is it possible that these percents are equal? Well, before we answer those questions, it should be pretty clear that we have to build a confidence interval based on the fact that we are asked to conclude something at 90% confidence. But we're not just building a confidence interval for a single population. We want to compare the difference in two populations' proportions. And so over here, I've got a setup on a how-to list. How to build a confidence interval for P1 minus P2. We can estimate the difference in two population proportions. Later in this course, when we actually begin statistics 2, FYI, we're just reviewing statistics 1 still, but later in this course we'll be able to compare more than two populations, but for now we'll just take it to 2. The good news is the flow for the confidence interval is exactly the same as it was before. Find a z, find a standard error, find a margin of error, and then find the interval. Finding the z is going to be exactly the same. We're going to stick the confidence level in the middle of a standard normal distribution curve and use the z-chart to calculate the z's that cut off the middle 90% from the two tails. In the second part, however, we'll have a slightly bigger formula for the standard error. As you can see, based on the structure, there's a reason I haven't completed it yet. But when we get to the margin of error, it's just going to be the product of the first two answers. In fact, we can go ahead and write that. Z times standard error. And I'm not sure if I've mentioned this before, but my z's have lines through the middle, so you know it's not a 2. And we find the interval, it's almost going to be the same as before. But remember, the underlying premise behind a confidence interval is to take what you get from your sample and stick the margin of error on it, both positive and negative, whichever way. So what's our point estimate here? Well, the point estimate is just the sample version of the population thing we're estimating. Since we're estimating the difference in P1 and P2, our point estimate would be the difference in P hat 1 and P hat 2, plus or minus the margin of error. But every confidence interval is structurally the same. Get something from the sample that's equivalent to what you're estimating for the population, stick a margin of error on it. So the only thing missing is the standard error formula, which I'll fill out in just a moment. All right, let's start by looking at this problem and seeing what we're given. Sometimes the things that we're given are pretty straightforward. We're given N1 is equal to 50. We're given N2 is equal to 40. But we're also given 10 men and 10 women. But those aren't actual values by themselves. They're values that we're going to need. think about the pieces that we're going to need. I know I haven't written this here, but we're still going to need the sample sizes, which we have, and we're going to need the p-hats, which we don't have. So we weren't explicitly given the p-hats, but we have enough information to calculate them. Remember, p-hat just means percent of a sample with a characteristic. In this case, the characteristic is you hold 2 or more jobs. For men, we would say p-hat 1 is out of the 50 men, 10 of them had 2 or more jobs. Well, 10 divided by 50 is 0.2 exactly. And for the women, the percent of that sample that has 2 or more jobs is 10 women out of 40, which is exactly 0.25. So in this sample, 20% of the men had 2 or more jobs, but 25% of the women. Does this mean that more women hold 2 or more jobs than men? Well, in this sample, yes, but is it strong enough to say this for the entire population? Hence the 2 questions. So those are the information, that's the information that we're given, and we're also given a 90% confidence level. Hard to do a confidence interval without one. All right, so what do we need to find? Well, what we need to find is this interval, but to get there, we have to jump through all the hoops. So let's start with step 1. Finding the z. We're going to put 90% in the middle, which means there's 5% in each of the 2 tails, because the remaining 10% gets divided by 2. Oh, I'm sorry. I was going to say pause the video and try this before I finish it, but I haven't given you all this formula yet. I should have said that in the last video. All right, so what z goes with 5%? Well, remember, in the z chart, the areas are in the middle and they have 4 decimal places. So we need to think of this 5% as a 4-digit decimal. The left area, let's go ahead and just write this here. The left area is 5%, so 0.05. And then stick 2 zeros. Let's see, 5%. I think that's, I'm going to double check. There are some teachers that will say, for these confidence levels, you should memorize these z-scores. And I don't have a problem with that, but I could throw a confidence level out of left field. That wouldn't be on your list of standard confidence levels and force you to use some way to get it. We're going to use negative 1.65. It's actually dead center between negative 1.64 and negative 1.65, but I've already explained why I use the larger digit. Using the smaller digit will reduce the confidence level. So we use negative 1.65 there, positive 1.65 there. Pretty straightforward. Now for the second step, to calculate the standard error. And here's the reason why I waited to give you the formula. The formula for this looks like the formula for one population. Remember, one population just had a single fraction. It was the square root of p hat times 1 minus p hat over n. But we have 2 populations, and therefore we have 2 samples. This fraction gets written twice. Once for the first population, so the p hats and the n's are subscripted with the 1s, and once for the second population. So plus the same fraction with 2's instead of 1's. P hat 2 times 1 minus p hat 2 over n2. So clearly a larger setup, but structurally it kind of looks right. Standard error for the first population, standard error for the second population. They look like they're getting added. They're not quite because of the square root over the plus, but let's not nitpick about the algebra. Let's just stick all the numbers in and see what happens. Again, if you're taking a test in my class, when you use a formula, write it with the value substituted so I can give you partial credit in case your calculator work goes wrong. All right, for the men, p hat was 0.2, so 0.2, times 1 minus 0.2 over the sample size for the men, which was 50, plus the same thing for the women, 0.25%, or 25% of them had 2 or more jobs. 1 minus 25%, that would be 75% who don't have 2 or more jobs out of the 40 women. And this goes into a calculator. I invite you to pause the video and try to put it in your calculator. This is where most people make mistakes on this problem, using these formulas for the standard error. Okay. I'm going to write down my answer, but then I'm going to put it into the calculator again. to 4 decimal places, I get 0.0888. Next digit is 1, but I'm going to do it again, and this time I'll enter it a different way. That's equivalent because I know a lot of ways to put things in calculators. And if you're in my class, the calculator requirement is you need one. I'm not going to require you to have a certain calculator, because if you don't, I'm not going to ask you to spend more money when you have a perfectly good calculator already. Yeah, I got the same answer twice, entering in 2 slightly different ways that were equivalent. So I'm going to assume that answer is correct. And there's our standard error. Now we can almost put it on cruise control, because the margin of error in a confidence interval, for the ones that we do, will always be the product of the first 2 answers. The z was 1.65. Our margin of error was 0.0888. And even though that would only have 5 decimal places, the 6th one would be 0. Even though that would only have 5 decimal places, I will always round to 4 decimals when I do a calculation, just for consistency. So to 4 decimals, 0.1465. Okay, so now what we have to do is find our interval by adding and subtracting that margin of error to our point estimate. Only problem is we really haven't calculated the point estimate yet, so we may want to do that first. P hat 1 minus P hat 2. In other words, the percent of the men minus the percent of the women. It was 20% of the men minus 25% for the women. So if we subtract that, we get negative 0.05. Now that's not our interval, that's simply the point estimate that we're going to stick the margin of error on. And don't be surprised that it comes out negative. We did a subtraction problem. When a subtraction problem comes out negative, it means something. It means the second number was bigger than the first. But this isn't our interval. Our interval is going to be that point estimate plus or minus our margin of error, which was right here, 0.1465. And I'm kind of running out of room, so I'm going to write the final answer after this last question mark in red so that it's easier to see. From 2. All right, so let's see what we get. Negative 0.05 minus 0.1465 equals negative 0.1965. And for the record, I could do a lot of this without a calculator. I'm only doing it with a calculator because I'm recording the video and I don't want to have to go back and make a, oops, I made a mistake video to follow this. I've done it before. And if we do the margin of, if we do the negative 0.05 plus the 0.1465, we get 0.0965. So from a mathematical perspective, that's a good enough answer. But since we were talking percents and we were asked to do some follow-up questions, we should probably think of this in terms of percents. So from negative 19.65% to 9.65%. And again, if you're wondering, well, why is it negative? Because we're estimating the answer to a subtraction problem, and that means something. In fact, let's see what it means. The first question was, can we conclude at 90% confidence that the percent of all men who hold 2 or more jobs is less than the percent of all women? Remember, we're estimating this difference. In fact, let's write it with men and women. That is the interval estimate for the percent of men minus the percent of women. Now, first question, can we conclude that the percent of men is less than the percent of women? Let's think about what that would mean. If this were less than that, then the answer to the subtraction problem would be negative. Let me say it again. If the percent of men were actually less than the percent of women, then the answer to this subtraction problem would be negative. We state with 90% confidence that the answer to the subtraction problem is in this interval. If the answer to the subtraction problem is in this interval, must it be negative? No. This interval contains both negative and positive values. Now, let's just say for kicks and giggles, it wasn't, but let's just say that both of these were negative. Then the answer would be yes. Why? Because we're stating with 90% confidence that this difference is in this interval and every number in that interval is negative, which means we're 90% confident that this is negative, which means we're 90% confident that the first number is less than the second number. But because this interval includes both positive and negative numbers, which is like saying it includes 0 and things on both sides of it, we can't say with 90% confidence that the first number was smaller than the second because it might be positive in this interval. But look at the second question. Is it possible that these percents are equal? Well, if the percents were equal, their difference would be 0. Is it possible for the subtraction problem to be 0? Yes, because 0 is included in this interval. This is usually what an interval for the difference in two things is used for, to try to answer the question, is it possible that one is less than the other, or is there a possibility that they're equal? Let me rephrase that. Is it likely that one is greater than the other, or is there a possibility that they're equal? If the interval is completely negative, then we are confident that the first number is smaller than the second. If the interval is completely positive, then we're confident that the first number is greater than the second. But if the interval spans between positive and negative, we're not confident of either of those things because it's possible that those two numbers are equal because it's possible their difference would be 0. When I type up for the people in my class, when I type the outcomes for this section, I will include those last three statements that I said. That if an interval estimating a difference is completely negative, then we are confident that the first number is less than the second number. If the interval were completely positive, this one's backwards, but if it were completely positive, then we would be confident that the first number is greater than the second number. But if the interval goes from negative to positive, we can't say either of those, but we can say that it's possible that the 2% are actually equal.